This is 2016 question 10b. It's a question on differential equations. So in this question, we're talking about a particle that moves along a line, and we can draw the line here, and its displacement from a fixed point O is described by the equation given. So we'll put O in here as well. And if you go down further, you'll see that the particle starts from rest. At a distance a. So these are two key things to get started. So a distance a from O, we'll put a here, and that's where the particle starts. So we call that t equals 0. That's when we start our stopwatch. We start our journey here. It turns out that this equation describes a motion known as simple harmonic motion, but we're not concerned with the details of that for now. We just want to solve the equation. Okay, so at any random point x along the journey as well, at any point x along the journey or any displacement x, the time is t. So time t is when your displacement is x, your displacement from the fixed point O. So now we can get started solving the equation. That's part I of the question, to find v. So we'll write the equation down here. So in part I, it's v dv dx is equal to minus omega squared x, where w or omega is a constant. Now at this stage we go through the three steps that we always do for this type of question. There are three defined steps. Number one is separate the variables, which in this case are v and x. Number two is integrate. And number three is find initial conditions. So initial conditions, and they enable us to get rid of the constant of integration c. So step number one, separate. That means get all the x's on one side, all the v's on the other side in our example. So v dv on this side, multiply both sides by dx, and you get minus omega squared x dx. And that's the first step actually already done in this case. That's easier than it normally is for this question. Now step two is integrate both sides. So the integral of v dv is the integral of minus omega squared x dx. And we can continue on with this. Omega squared is a constant, and any constant can go outside the integral sign. It doesn't affect the integration process. So we can now rewrite it as integral of v dv is equal to minus omega squared integral of x dx. From the rules of integration, we can, the left-hand side becomes v squared over 2. You increase the power by 1, divide by the new power. Minus omega squared stays as it is. And x, the same rule, increase the power, divide by the new power, so it becomes x squared over 2. And don't forget plus the constant of integration. And that's step 2 done. Integrate, so separate is step 1, step 2 is integrate, and now step 3 is initial conditions. So it's ICs for short. Okay, so now we go back to the start and the information we're given, and we see that at the start, in terms of v and x, when x was equal to a at the very end here, when x was a at the end point, the velocity, let's see what, the velocity was 0. We should have stressed that at the start here. The particle starts from rest, so that means that v is 0. Rest means no velocity. So at this point over here, v is 0. It starts over here. So v is 0 when x is a. V equals 0 when x equals a. And you sub those two into our equation and see what happens. So it's 0 squared over 2 equals minus omega squared into x squared over 2. So x squared is a squared over 2 plus c. And that gives us, if you, so this is not, this is just gone now, so C becomes, if you take the minus across as a plus, you get omega squared A squared over 2. Now that we have a value for C, we put it back into the original equation. So the original equation is here. V squared over 2 is equal to minus omega squared x squared over 2 plus C, which we just worked out to be omega squared A squared over 2. And now we can tidy all that up a little bit. The 2's can just cancel. And the V squared becomes, take out the omega squared, it's a constant, just take out the constant term here in both, the constant in both terms. That's omega squared. So omega squared into whatever's left over is A squared minus omega minus x squared. So that's V squared, omega squared into A squared minus x squared. Now, that means we can get V by getting the square root of both sides. So the square root of all this is the square root of omega squared into A squared minus x squared, which becomes simply omega root A squared minus x squared. And that's what we were asked to do. If you go back to part I, we were asked to find an expression for V in terms of A, omega, and x. And that's what we've done. Now in part 2, we have to get x. So we're going to take the answer for part 1. So in part 2, V is equal to omega root of A squared minus x squared. And we can now go back to our definition of V, which is basically velocity is distance over time or displacement over time, rate of change of displacement. If you write that in derivative form, it's dx dt. So now V is dx dt. And we go through our same 3 steps again, which are separate, integrate, and initial conditions. So separating first, multiply both sides by dt, and you get dx is equal to omega root A squared minus x squared. That should be a square there. Dt, multiplying both sides by dt. So both sides multiplied by dt. And you get dx on this side. Now, that's the separation, or actually it's not done yet. We now have to divide across by the root of A squared minus x squared. So divide, we put a 1 in front here, maybe it's easier. Divide both sides by the root of A squared minus x squared. And now that's gone. So the whole point of this, again, is to separate the x's and the t's. X on one side and the t's on the other side. So now we have it done, we have the separation done. 1 over the root of A squared minus x squared dx on this side is equal to omega dt on the other side. Now integrate both sides. Integral and integral over here. And that becomes integral of, well, this is another special integral from the table. If you go to your tables, you will see that if you integrate inverse, if you integrate 1 over the root of A squared minus x squared, that becomes inverse sine of x over A. So that's in the tables. So if we apply that rule here, on the left hand side becomes the inverse sine of x over A. So the A in the formula in the tables has been replaced by a capital A in our question. And that's equal to, on the other side, you can take out the omega outside the integral, and it's the integral of just dt. And then you put a 1 in there. So there's nothing else left. And now we can say it's omega integral of 1 becomes t plus c. Now, also at this stage, we can write that in reverse order, so we can actually go and write the sine of omega t. Well, first of all, actually, sorry, we need to look at initial conditions, of course, as well. Let's go back now and look at the initial conditions for t. So just to remind ourselves, at the start, t was naught. We're talking about t and x here, so at the start, when x was a, t was naught. So when x was a, t was naught. So the initial conditions, when x equals a, t equals naught. So you put those in and you get inverse sine of x over a, which is a over a, is equal to omega t, which is omega into 0 plus c. And that's gone. And now c is the inverse sine of 1. And from your tables again, or from your calculator, the inverse sine of 1 is pi over 2, 90 degrees. So the sine of c equals 1, so c is pi over 2. And yet again, once you've got c, you put it back into the original equation, which is up here now. So inverse sine of x over a is equal to omega t plus c, which is plus pi over 2. And we can write it in reverse as well. So that means that the sine of double omega t plus pi over 2 is equal to x over a. And finally, multiplying both sides by a, you get x is equal to a sine of omega t plus pi over 2. And that's what we were asked to do, find an expression for x in terms of a, omega, and t.